Okay. Let me start the second part of this lecture with this slide. This slide shows the phase margin, gain margin altogether. In the past, we discussed gain margin and the phase margin individually, but here we are considering two margins together, altogether. So this is the phase margin, and this distance is related with gain margin, and those two margins are shown in the polar plot, and the same margin, gain margin, phase margin can be shown in the polar plot. So they are the same information, but in different format. Okay. So this one is easier to understand, and this one is easier to evaluate gain margin and the phase margin. So most students or most people, they forget about this and they are remembering this, and some teachers, some professors, they are only explaining this without any background about this polar plot and Nyquist analysis. Maybe they are assuming the student know many things, which is not true, okay, for most cases. Some professor, they skip the whole thing about the Nyquist stability criterion and the Bode plot, and they teach something very strange, some useless things, okay, like sensitivity or something. All right? Okay, so take a look at this. Assume this is the original polar plot of system, maybe for our case, the converter. So converter is stable because this polar plot crosses this minus real axis in the line segment A. So this is stable. And if it passes this critical point, then system is marginally stable. And it passes this outside of this part that indicates the system is unstable. Okay. So now system is stable, but suppose you introduce the phase delay while maintaining the magnitude constant, that means this plot, this part is simply rotating in clockwise direction. That means if this is rotated this much, it passes this critical point and becomes marginally stable. So the phase difference between this minus 180 degree and the phase at this point means this polar plot is passing the unit circle, means the magnitude of polar plot becomes unity, and this the difference between minus 180 and angle at this frequency at this point is defined as the phase margin, pi m. Okay, this is obvious, right? Because this margin. Okay, and for the gain margin, this is the original polar plot of the loop gain. Suppose this is the 0.5 minus 0.5, then you increase the gain twice, then this will pass this. Right? So for this case, the phase remain the same. That means phase remain the same. So there is no rotation at all, and just stretching out this line segment in this direction. Okay, expanding out to this direction. How much we can go is related with the distance between this critical point and this point. This point is the loop gain magnitude when phase of loop gain drops to minus 180 degree. Okay, that is the definition of this gain margin. So this is obvious, and gain margin is this one, 20 log 1 divided by k. K is the coordinate of this. Actually, coordinate of this rectangle is minus, this square is minus k, comma 0. So k is smaller than 1 by definition. Then if this k is smaller than 1, then if you use k instead of 1 over k, then this becomes negative number. Okay, so margin becomes negative number is a very strange thing. So to avoid that, to have positive margin for the stable system, it comes here. So this is the relationship, and this is expressed in log scale, and this is just this conversion of this log scale to the linear scale. Okay. For example, if k is 0.1, maybe the crossing point is somewhere here, then you calculate this, then this gain margin is 20 dB. When k is 0.5, this becomes 20 log 2, which is very close to 6 dB. Okay. So if gain margin is 26 dB, then you calculate this. This is 0.05. Then maybe the crossing point is somewhere here, very close to origin. So you have a huge margin, okay, relatively large margin to increase the magnitude with the fixed phase characteristics. Okay. So from this polar plot, this phase margin as gain margin can be immediately seen. Same is true here. This is the Bode plot of this same information. Okay. So at low frequencies, phase is somewhere here. Phase is somewhere here, and the magnitude is very large, very large. At high frequencies, it goes to approach to this origin with minus 270. So there is a phase. Okay. All right. Let's think about the phase margin first. When you are evaluating phase margin, you find out this point where this polar plot length is just 1. That is the same as this crossover frequency. Okay. At 0 dB crossover frequency, you compare with this minus 180 degree and the phase of the loop gain at that frequency, which is this, and the distance between this and this is phase margin. Okay, exactly same information with this one. Okay, so the phase margin means if you add, okay, you have phase margin of this much, so you introduce the additional phase delay of this much. It's not working. Okay, let me move this to here. Okay. Then you introduce additional phase delay uniformly for all frequencies. Then you get this point. Okay. That means you have this much of rotation. Then system becomes marginally stable. That means at this point, when phase drops to minus 180, the magnitude becomes unity. There is a borderline between stability and instability. So if you have this kind of plot, Bode plot, just find out this point and calculate or estimate the distance between this and this. Very easy, right? Okay. And then think about this gain margin. Gain margin is determined the distance related with this point and this point. So this minus real x cross point is determined at this frequency. Okay. At this frequency, phase drops minus 180. Then magnitude should be smaller than unity. That means this is passing this part, line segment A. Okay. And the distance is related with gain margin. So distance is this one. So you fix this. You keep this and increase phase this much uniformly for all frequencies. That becomes this situation. And then this, when phase drops to minus 180 degree, magnitude is 1. Okay, that is the condition for the borderline between stability and instability. And one difference is, for this point, the oscillation frequency is this one, and at this case, oscillation frequency is this triangle. So this oscillation, of course, is much faster than this one, higher frequency oscillation. This one is relatively lower frequencies. Okay, so this is about the gain margin, phase margin considered all together. Okay. Maybe this is the original definition of gain margin, phase margin shown in the polar plot, but it can be transferred this equivalent shape. Okay, but practically you will be seeing this, right? So because the simulation result or the impedance measurement output, usually they show this frequency response in Bode-Plot format. Okay? So if you see this from your measurement or simulation, then you can directly evaluate the phase margin and the gain margin. Okay? If you want, you do the simple program or a simple calculation or a simple spreadsheet type, you can transfer this to this, and from this you can read out these two margins, which is the same as this one. Okay. Okay. And the stability margins are determined as the measure of margin. So how much margin I have? I'm in the stable. I have the stable system. Then how easily the stable system becomes unstable. That is the concept of the margin. So originally it is divided, it is defined to specify the degree of the being stable. But this is very important. Stability margins can be used as the metrics for the closed loop performance of the system. Particularly the phase margin is very important. That is of the prime importance when you are considering the closed loop performance of your system. So idea is this one. You have several polar plot trajectory. So these blue ones, they don't touch this, and they pass this line segment A. So all of them are stable. Okay, but this is phase margin. For this case, phase margin, they are very small, and this distance is very small. So gain margin is very small. So when your polar plot approaches this point, this critical point, it passes near this point somehow. Maybe it can go like this. Then still you are stable, but there is some problem. Okay. So proximity or nearness to this critical point in polar plot indicate the small phase margin and the small gain margin. Okay. So when it passes this point at this omega equals omega c frequency, the pole of this closed pole or root of characteristic equation has one pole here and one pole here at j omega c and at minus j omega c. Okay. So for that case, you know, this will generate the sinusoidal oscillation at the frequency of this one. So if it passes this, okay, then pole is here, but it does not pass this, and it is inside of this, then this the root of characteristic equation or system poles are located in the left-hand side. So you are safe, but very near to this point that create very oscillatory behavior. Okay, and it produces the peaking because this indicates there is a small phase margin and gain margin, and you prove this later. Okay, I think this was the one problem in the in-class final exam of last semester. This one. Okay, so you have this relationship. If PM is small, very small, this will be large. Okay. If PM is smaller than 60 degrees, this becomes larger than unity. So you will be seeing peaking. If PM is 0, then cosine 0 is 1, then they cancel and the denominator becomes 0. So you have infinity peaking at this frequency, okay, at omega c. This is the frequency at which magnitude of loop gain becomes unity 0 dB crossover frequency, okay. And another case is gain margin. If you have small gain margin, you can you prove this, okay. It's not difficult. Just think about the definition of the gain margin. And at that point, if gain margin is small, and this peaking, if gain margin is 0, then this becomes 1, then denominator becomes 0, or then also peaking will be infinity, and this peaking occurs at the frequency where phase drops to minus 180 degree. Okay, very similar but different. So because usually this frequency comes later, oscillation or peaking due to the gain margin occurs at higher frequency compared to the oscillation or peaking caused by small phase margin. That is okay. That is okay. So, and this induces oscillatory behavior in the transient response for two different regions. But they are the same. They have the same origin, but interpretation can be different. Because of this peaking means there is a second order term, undamped second order term that will produce the oscillation at particular frequency. We already discussed the oscillation frequencies. Okay. Another interpretation is with small phase margin or gain margin, the trajectory approach this point, then the pole root of the characteristic locate near the imaginary axis, but in the left plane. At that case, the oscillation will start. Okay, oscillation emerges. Okay, because at this frequency, we confirm that through the simple equation. If pole is located at this point, there is a sustained oscillation at this frequency. Okay, by extending that idea, you can easily confirm this, or you can easily predict this. There are two different regions, but they have the same origin. Okay. All right. So phase margin and the gain margin is important, and the phase margin is more important. So phase margin is the prime metric for the closed loop performance of feedback controlled system. So here is one example. I did several simulations, and for each simulation, the phase margin is gradually decreasing by some 15 degrees, something like that, and the crossover frequency remained the same. Okay, I intentionally selected this case to show impact of the smaller phase margin. So this is a minus 180. So phase margin is decreasing like this. Okay, and if you take a look at this is the trajectory of polar product of loop gain. So it crosses the unit circle at different frequencies, and it approaches to this. Okay, the magnitude has not changed. I just gain margin remained about the same. I just adjust the phase margin unit step fashion decrease. Okay, so this shows the same information. This is the direction of the smaller phase margin, direction of the small phase margin. And if you take a look at the output impedance, if the phase margin is sufficiently large, you have phase margin larger than 60 degrees, then output impedance will be like this. Okay, this is a very nice output impedance, and transient response will be very nice with the first order characteristics. Okay, for this case, and this is gradually reduced, and it generates peaking. Peaking means there is some oscillation at this frequency, decaying oscillation, and the decaying rate becomes slower if the peaking grows larger. Okay, and this is the relationship between peaking, magnitude of the peaking, and the phase margin. We'll discuss this later. This is in dB scale. dB scale. I have an example of this. Okay, so this is the transient response, step load response at the phase margin of 60 degrees. Basically, this is first order system, and this time constant tau is 1 divided by omega p, and omega p is this one, you connect two asymptote, and this is the omega p. So this determines the settling time and so on. And if you decrease the phase margin to this one, it shows some tint of oscillation. If you further reduce this, then it shows growing oscillation, and eventually this is unstable. So phase margin is smaller than 0 degree, maybe negative phase margin. Okay. And the frequency of this oscillation occurs at omega c. Okay, because that is the frequency of peaking. Also, that is the frequency of loop gain crossover, 0 dB, crossover of loop gain magnitude. So, as the rule, general rule of thumb, phase margin is something in between 45 to 60 degree is good, very good. Okay, you can increase this to 80 degree, 90 degree, then you should pay some price. Your other performance will be suffered because of this. And the gain margin should be larger than 6 dB or more conservatively larger than 12 dB. This is twice and this is 4 times. Okay, this is important. All right. But it also depends on the characteristic of the loop gain. So in the around the crossover frequency here, maybe loop gain slowly changing very gradually like this. Then this phase margin or this gain margin is okay. All right. But if the loop gain crossover frequency near that one, this is changing like this, then means phase is changing abruptly and the gain is changing fast. Okay, then this number does not mean much. Okay, so to have safe and robust this stability margins, crossover frequency does not occur when this slope is fast. Okay, so usually -1 slope is desirable. -1 slope. Okay, -2 slope is very dangerous. -3 slope is surely the system is unstable, and with the larger slope or steeper slope, phase is changing more abruptly. That means the margin will run out very soon. Okay, if there is some minor disturbance or minor tolerance, then the converter is unstable. Okay, so don't trust only this number. You should take a look at this slope. Okay, this one is also bad. Suppose you have this kind of slope, flat one. This one is very bad. This one is also bad. Okay, because there is the gain margin will be very small. So at higher frequency, due to the small gain margin, there should be the peaking. Okay, so this is not desirable. This magnitude. And this is not desirable, this -2 or -3 slope, and this one is okay. This one is acceptable one, then this number, this margin mean much. Otherwise, they're just a number, and that number becomes very sensitive to the variation or something, then you are not fully confident with your judgment. Okay, so this is the end of topic 4, and let me show just one page, introduction of the next topic. So you will have 2-week break. Okay, so there is a long break. So after break, we'll be starting talking about this modeling, right? So there are 2 steps of the modeling. One is average modeling to derive the circuit model, circuit shape, structure of the circuit, which predicts the average time domain dynamics. And later on, linearization is coming up. then this will provide you small signal model. If you have a small signal model, you can use small signal model to analytically calculate and predict all the discussions we went through using the measurement or simulation empirical method. Okay? So after 2 weeks, we'll study this, and this will be followed, and this will come up. All right? Okay, we stop here. Okay. Okay. Thank you for your attention. Have a nice, happy, long break, 2-week break. Okay.